This is a set of tutorials using FLAC3D to calculate the total and effective stresses for a homogeneous embankment dam with rock abutments. This set of tutorial videos provides an extension of the FLAC2D tutorial Embankment Dam that had modeled the problem to the left. In this new set of tutorials in FLAC3D, a more complex geometry shown to the right will be modeled. Note that the geometry of the embankment dam in the stream direction modeled in FLAC3D will be the same as the tutorials in FLAC2D. In addition, the properties of the embankment dam remain essentially the same. The additional geometric complexities that will be modeled in FLAC3D are highlighted here. In this new model, the crest width of the dam will be 3 embankment heights, and the channel width will be a single embankment height. The adjacent rock abutment and foundation will be modeled with 20 feet of foundation rock below the embankment, and 15 feet of the rock abutments to the right and left. This set of tutorial videos have been developed to incrementally lead to calculating the total and effective stresses of the complex geometry shown and have been broken into 3 parts. In this current first video, the command script in FLAC2D will be modified for FLAC3D, and a numerical mesh that includes a 65-foot width of the embankment will be used. The numerical mesh of this model, Model 1, will be developed using the extrusion with sketch set. In the next tutorial video, the steps to develop the numerical mesh of the more complex geometry using building blocks will be presented. The numerical mesh of this model, Model 2, will include the embankment with the rock abutments. In the last tutorial video, the numerical mesh for Model 2, with modifications of the analysis script for Model 1, will be used to calculate the total and effective stresses of the embankment dam with the rock abutments. Please note that for both numerical meshes, the models have been developed to have less than 1,000 numerical zones and therefore can be completed using the free demonstration mode version of FLAC3D available. We now focus on the development of Model 1. Recall the sketch input parameters from FLAC2D, which are shown here. The edge type group names along the boundary of the embankment are shown. Also, now needed in FLAC3D is the out-of-plane dimension, in this example 65 feet. Also, it will be advantageous for later command assignments to define face groups along the left and right side, here named side. Please note that a total of 5 numerical zones in the out-of-plane direction will be used to model the 65-foot width of embankment. The location of the points along the boundary are shown here. The points are the same as those used in FLAC2D. As with the FLAC2D example, the mesh configuration will be controlled using the zone number object property for each of the 7 edge groups. The values that will be used for each of the 7 edge type groups are provided in the table shown to the top right. Note that fewer zones are specified along the surface here in FLAC3D than in FLAC2D because the desire to still have the FLAC3D model run using the demonstration mode version of FLAC3D with the additional numerical zones in the out-of-plane direction. It is now time to use the sketch tool to develop the numerical mesh. In this tutorial, the edges from FLAC2D will be exported and opened in FLAC3D. Please note that if the analysis in FLAC2D has not yet been completed, the points and edge groups can be created in Sketch in FLAC3D in the identical fashion as in FLAC2D. For step-by-step details, please see the FLAC2D set of tutorials. The set of graphic-based interactions with FLAC3D to produce the numerical mesh in Sketch will now be shown. At this stage, the zones for the numerical analysis have been produced. Zone face groups have been created along the surface except for the left and right sides. To add a zone face group to the left and right sides of the mesh, here called side, the following graphics-based interactions are used. The last step before moving to the analysis commands is to save the state, here called mesh.save, so that it can be restored in a data file. The analysis commands to calculate the total and effective stresses and water flow in FLAC3D will now be provided. Because of the commonalities in commands between FLAC2D and FLAC3D, most of the command script in the data files from FLAC2D provided in the previous set of tutorials can be used in these FLAC3D analyses. The commands in the data files in the FLAC2D tutorials will now be presented with highlighted changes needed for use in FLAC3D. First, revisit the data file one_staticanalysis.dat. The first two commands that will be changed for use in FLAC3D include the fixity conditions along the base of the model, that is now vel 0, 0, 0, and a more specific specification of the direction of gravity, that is now 0, 0, minus 32.18. One command that needs to be added for FLAC3D is to specify boundary conditions along the two sides of the embankment. The modeling decision here is to allow the sides of the embankment to be free to move in the stream direction x and vertical direction z, but fixed in the autoplane direction y. This specific boundary condition is achieved with the zone grid point fix velocity-y 0 range group side command. The next file to consider is 2_seepage-analysis.dat. Two changes to this data file for use in FLAC3D are needed. The first change is reassignment of the mobility coefficient to account for the fact that z is now vertical and x and y are horizontal. That is now permeability-yy 7.21 e to the minus 10, permeability-zz 2.56 e to the minus 10. The second change is reassignment of the pore water pressures, with pore water pressure changing with z and not y. That is now gradient 0, 0, minus 62.4. The next data file 3_flowcalculations.dat from FLAC2D can be used exactly in FLAC3D, requiring no changes. Note that the value of flow_value computed in FLAC3D will be 65 times the value in FLAC2D because of the outer plane width in FLAC3D of 65 feet. The last data file 4_updatestresses.dat requires only one change for use in FLAC3D, reassignment of the surcharge due to the pore water pressure, with the surcharge on the embankment changing with z, not y. That is now gradient 0, 0, minus 62.4. The set of analysis commands presented in the last four data files will now be opened and run sequentially in FLAC3D. Each data file will be run by clicking the green arrow or simply clicking Ctrl-E. You will see a cycling info dialog box that presents the results during cycling. Note at the end of each data file, the model results are saved for that particular stage of the analysis. The analysis results from FLAC3D can now be reviewed and assessed with a series of plots. A highlight of a few of the plots that could be created in FLAC3D are now shown. This completes the first tutorial video in FLAC3D for the homogeneous embankment dam, where the FLAC2D analysis previously presented was modified in FLAC3D to model a 65 width of embankment. In the next tutorial, the steps to develop the numerical mesh of the more complex geometry using building blocks will be presented. In the last video, the numerical mesh created using building blocks, with modifications to the analysis script created in this tutorial, will be used to calculate the total and effective stresses of the embankment dam with the rock abutments.